Alright class, so last time we started talking about thermodynamic part 1. Now let's go to thermodynamic part 2. Now reaction. We want to predict if a reaction will happen or not. What information is needed to make that prediction, to predict if a reaction is going to happen or not happen? The first information that you need, if the reaction is going to happen or not happen, you have to look at energy. You have to look at the delta H of the reaction. And we've talked about that so much. You have to look at the delta H of the reaction. And if you remember, we said when you have a delta H of a reaction, you have two options. You can either have a positive delta H of the reaction, which means the reaction is endothermic, or negative, which means the reaction is exothermic. Okay? Alright, now which one is favored? We said exothermic reaction, this is favored. Why is it favored? Because not only you don't require energy, you're releasing energy to your surrounding. So endothermic, you require energy. This one, not only you don't require energy, you're releasing energy to the surrounding. So that is going to be favored. Now here's the thing. There are endothermic reactions that do happen. Because some reactions are endothermic, some reactions are exothermic. So even though exothermic is favored, but we do have reactions that are endothermic. So there has to be a second component to predict if a reaction will happen or not happen. It's not just based on is it endothermic or exothermic. Now that second information, the second component is entropy. And you had the delta H of formation, the delta H of reaction, the enthalpy in Chem 1A. Now in Chem 1B, we're going to be a little bit fancier. We're going to talk about entropy, which is delta S. Entropy is delta S. Now let's talk about entropy. Let's talk about this delta S. Okay. Now, what does this mean? What does this little thing mean that I put in there? That means standard. That means that a standard condition. Standard condition for reaction is 25 degrees Celsius to 98 Kelvin because we do reaction at room temperature. Is different than STP for gases. Standard temperature for gases is 0. But is 0 degrees Celsius. But for reaction, because we do reaction at room temperature, is 25 degrees Celsius. But the pressure is 1 atm. So this little knot means standard, and these are the things. All right. Now the unit, it has a unit. Delta S has a unit. The unit for S for entropy is joules over Kelvin times mole. Okay. All right. Now, what does it mean? What does it mean? What does entropy mean? What entropy mean? Entropy means randomness. Entropy means randomness. Let me write it down. Randomness. What entropy is a measure of order. So it's a measure of disorder. So it's randomness is a measure of disorder. And I will explain what I mean by this. So entropy, S, again, at standard condition with 25 degrees Celsius, 1 atm. That's the unit. What does it mean? It's a measure of disorder. Now, when I have delta S could also be plus or minus, just like enthalpy. And opposite of enthalpy, if you look over here, for the delta H, we had endothermic, exothermic, and exothermic was favored. Here, for delta S, the positive is favored. The positive is favored. Now, let's go over exactly what does this mean, measure of disorder. What does this positive, negative mean? Let's do an example. Here's an example. Let's say we have solid, and a solid is going to go to gas. So we have solid, the solid is going to go to gas. Now, solid, if you have a piece of solid that has a good order, is ordered, is nicely packed together. Whereas gas, we would consider to be disordered, right? There's some disorderness to it because gas, they're randomly moving around or far away from each other. So solid, I'm going from order to disorder when I go from solid to gas. So what do you think the delta S would be? Would it be positive or negative? Now, the delta S would be positive. The delta S would be positive. So when you go to the disorderness, when you go to something that is more disorder, your delta S is positive. Now, that's interesting. That means being messy, being disordered is favored. Nature wants to be messy, right? It's easier to be messy than to be, to be ordered. So nature is just like us. Now, let's say I have gas. I'm in a gas form, and I go from gas to liquid. So if I do that, again, gas is more disordered, right? Because gases are moving around or far away from each other. Liquid is more ordered than gas. So I go from disorder to order. If you go from disorder to order, your delta S is gonna be negative. So delta S is a measure of disorder. So if you have positive, that means you go from order to disorder. If you go disorder to order, is negative. And is favored to be messy, is favored to be disorder. So remember that. So far, so good. Okay. Now, I looked this number up. Cesium gas, the entropy is 175.6 joules over mole Kelvin. And cesium solid, the entropy is 92.07 joules mole Kelvin. Now, here's a question for you to talk it out. I know we're not in class anymore, but maybe we can talk it out with your roommate, even if they have no idea what chemistry is. Does this make sense to you? Does this make sense to you? It does make sense. Which one is a larger number? They both are positive, right? So they both are disordered. Which one is more disorder? Because remember, entropy is randomness, it's a measure of disorder. Which one is more disorder? This one right here. And gas is a lot more disorder than solid. Solid is more ordered because you have all this solid packed together. Whereas gas, no, you're disordered, you're moving around, they're all getting far away from each other. So does these numbers make sense? These numbers make sense because this one is more disorder, so it has a larger value going on. So far, so good? Okay. All right, so let's do a little exercise, yeah? Let's do a little exercise. It's been a while since we've done exercise. CH4 gas, C2H6 gas, C4H8 gas. And I'm going to say this is A, this is B, and this is C. Okay? Now, here the entropy numbers: 186, 310, 229. Again, let me see. These are all in joules over Kelvin mole. Okay? Match this up. Match these numbers to these. Alright, pause me and match them up. Alright, now if we had to match this up, how would you match them up? So they're all gas, okay? So they're all gas. So they all are disordered because they're all gas. Now, what's happening as you go from methane to over here? What happened to butane? What's going on? You get more complex. Do you agree? As you're coming down A, B, C, you get more complex. Now, what does complex mean? When you're more complex, you are more disordered. Because now you have more of these things. So you have more carbon, more hydrogen to deal with. So you're getting more disordered. So if we had to match, 186 would be A, 310 would be, oh, what did I just do? 310 would be C, and 229 would be B. Okay, so again, more complex you get, the more disorder you get. Now remember, and I talked about this before, I want to mention it one more time because I need to really understand that. So when you're matching these things, the lowest number is either going to go with the simplest one or the most complex one, right? So then you have only 50-50 option, which is good option. All right, so hopefully entropy makes sense. A measure of randomness, disorderness. Nature wants to be messy. We want to be messy. So when the delta S is positive, means disorder, and that is favored. Okay, now let's do a practice problem. Here's our equation. Propane, which is C3H8 plus 5O2 gas, goes to 3CO gas plus 4H2O liquid. This is a combustion reaction. Now I want to give you the entropy value in joules over mole K. Okay, and the entropy values, I looked them up. I looked up these values. I wouldn't know until I look them up. You can look them up in your textbook. So I looked them up. All right. Now what I want to do, I want to find the delta S of this reaction. You remember how we figured the delta H of the reaction? It was product minus reactant using delta H of the formation. The delta S is exactly the same thing. Product minus reactant is exactly the same thing we've done before. So you can even pause me and do this and then check your answer. So product minus reactant, the same thing before, just like the delta H of the reaction. So I have the carbon dioxide is 213.7 joules over mole Kelvin. Except you don't forget, we have to care about the coefficient, right? Because there is a mole component in there. So it has, I times it by 3. I times it by 3. Why do I times it by 3? Because the coefficient matter. So I'm going to add up all the products together. And then it's 69.9 joules over mole K times 4. Okay. Again, the coefficients do matter. So that is all my product. Product minus, I go to my reactant, 269.9 joules over mole K. And it just times 1 because I only have one propane, plus 205 joules over mole K. And I want to times it by 5 because that's the coefficient. Because you have to times it by the, and it was only 1. So product minus reactant. Let me write it in red. Product minus reactant. Nothing you hadn't seen before. This was 1. So make sure you put in your calculator so you get the right number. It would be negative 374.2 joules over K because the moles cancel out, and that is my delta S. That's my entropy. Okay, now I want you to pay attention to this one over here. The number is negative, so that means what? We became more ordered or became more disordered. The number is negative, so that means we became more ordered, right? Because positive, that means disorder. Positive means disorder. We talked about it right here. Positive means disorder, and that is favored. Now over here is negative. Negative means is more ordered. Now does that make sense that this is negative? If you didn't have this number, if you hadn't done this, could you guess that the delta S is going to be negative? You could have. Here's how. Let's look at this. We could have not done this conceptually. I mean, we won't have numbers, but it's still a pretty good indication. I have one gas molecule and I have 5 O2. So all together on this side, I have 6 moles of gas. Now, let's go to the other side. Over here, this is water is liquid, so no. I have 3 carbon dioxide gas. So it goes from 6 moles of gas to 3 moles of gas. I have more gas here, and gases are disordered. I have less gas here. So what did it become? It become more ordered, right? It became more ordered. If it becomes more ordered, the delta S is negative, right? If it becomes more ordered, the delta S is negative. So we could even predict the delta S is going to be negative just by looking at the number of the moles of the gas. More gas means more disordered. Less gas means more ordered. So we went from more disordered to more ordered. That means the delta S is going to be negative. So far, so good. All right. Beautiful. Let's do another practice problem. 2 H2O liquid goes to 2 H2 gas plus O2 gas. Here's what I want you to do. Predict the delta S, the sign for delta S. What's going to be the sign for delta S? Pause me, figure it out, and then we'll talk about it. On this side, I have 0 gases. I have no gas. On this side, 2 and then 1, I have 3 gas. So you went from no gas to 3 gas. What did you become? You become more disordered because gases means disorder. So you became more disordered. If that's the case, what is the sign for delta S? Then the sign for delta S would be positive. Disordered means positive. Okay. Now, often, not always, you can predict the sign by looking at moles of the gases and see what happened. You have more, you got more gases, or you got less moles of the gases. So, not all the time, but often you can predict the sign by looking at the moles of the gases. And you can also look up the S value, the entropy value, and actually do the calculation and then figure it out. So far, so good. Okay. Now, I want to summarize what we talked about. So, everything that we talked about, basically, we're trying to figure out if a reaction is spontaneously would happen. To determine if a reaction would spontaneously happen, we have to look at 2 things. We have to look at delta H, and we have to look at delta S. We have to look at both delta H and delta S to see if a reaction will happen or if a reaction will not happen. Now, let's do a practice problem. N2 gas plus 3 H2 gas goes to 2 ammonia gas. Okay. Now, I want to give you the delta H of the formation in kilo. Give me 1 second. Let me have more room. I want to give you the delta H of formation in kilojoules per mole. And then I'm going to give you the entropy value in joules over mole Kelvin. Okay? So I'm going to give you these numbers. The delta H of formation for N2 is, I haven't looked it up, you should be able to notice, is 0 because delta H of the formation, that's how you make it from its pure element. N2, that's how it exists in nature. So the delta H is 0. H2 is 0. That's how it exists. That's how the pure form exists, is H2. So it's 0. Ammonia, I had to look it up, is negative 46.11. The entropy, 191.61, 130.68, and 192.45. Okay. Now here's what I want you to do for this reaction. What I want you to do, I want you to calculate the delta. I want you to calculate the delta H of this reaction. I want you to calculate the delta S of this reaction. And lastly, I want you to predict, will it happen? Will this reaction happen? Okay, you know how to do this. You have all the tools. Pause me and then do this on your own. Okay, now that you unpause me, let's go one by one. Delta H of a reaction. You know we do product minus reactant. You already know that. You have all the value that is given to you on here. All the values are given to you. You go product minus reactant. Add up all the product, add up all the reactant. Do not forget to multiply by the coefficient so the moles can cancel out. So I ended up having minus 46.11 times 2. Okay, that's my only product. Minus, let's go to reactant. Reactant is just 0 and 0. Product minus reactant. What I end up getting is negative 92.22 kilojoules. Again, moles cancelled out. Moles cancelled out. I have this. Moles cancelled out. Don't forget that. Now, to do delta S of the reaction, the same thing. Product minus reactant. If I go over here, I'm going to add up all the product. 192.45 times 2. That's my only product. Minus, to look at the reactant, 191.61 plus 130.68 times 3. Okay. Product minus reactant, add up all the product, add up all the reactant, subtract them, I get 198.75 joules per K. Again, moles cancels out. Moles cancelled out. Will this reaction happen or this reaction will not happen? What do you think? Here's what I need you to remember. And I'm going to write this down because you got to remember this for me. You got to remember this for me. If delta H is negative, that means it's favored. Exothermic reaction is favored. Is delta S is positive, that is also favored because this order is favored. This order is favored. And exothermic, when you release energy, is favored. Okay. So, these are my favored. So let's come over here. Delta H is negative. Exothermic reaction is favored. That is great. So what I'm going to do, I'm going to put a happy face over here. Because this is negative, is going to be favored. Delta S is also negative. Delta S, if it's negative, is not favored because that means we are ordered. So I'm going to put a sad face. Okay, one is favored, one is not favored. What will happen? Will the reaction happen or not happen? If both were favored, if I had a minus plus, the reaction will happen. If both were not favored, the reaction will not happen. But what happens if one is favored, one is not favored? Will it happen or will it not happen? Every time you have in that situation, one is favored, one is not favored, you have to look at Gibbs free energy to see which component is going to win. Here's Gibbs free energy. Delta G equals delta H minus T delta S. What it does, highlight this equation, it looks at the balance between the two components. It looks at the balance between the two components. Okay? Looks at the balance between the two components. And don't forget, at a standard condition, I'm going to write this down, at a standard condition, the temperature is going to be at 25 degrees Celsius or 298 Kelvin. Don't forget that. Okay. Now, let's plug in those numbers from before to figure out delta G. Now, here's the thing. You have to make sure that the units are the same. Okay? You have to make sure that the units are the same. Now, you can use both of these joules or both of these kilojoules, but it have to be the same, right? So here I have kilojoules and here I have joules. But pick one. Convert the kilojoules to joules also, or convert to joules to the kilojoules. But they have to match. It doesn't matter which one it match as long as it's matched. I'm going to convert it to joules. So my delta H is going to be minus 92220 joules minus, now every time we have a standard condition, and usually it is a standard condition, the T is 298 Kelvin times my S was minus 198.75 joules per Kelvin. So again, the Kelvin cancels out and I convert that one to joules, so they both are joules because units matter. So what I end up getting is negative 32992.5 joules. Okay? Or I can try to convert it to kilojoules because it's a nicer number. That would be negative 32.99 kilojoules. That is my delta G. Okay. Now let's talk about the delta G. The Gibbs energy could be minus or it could be plus. If the Gibbs energy is minus, that means it's favored. Plus is not favored. So, will this reaction happen? Yes, this reaction will happen. This reaction over here, over here. This reaction over here, will this reaction happen? The answer is yes, because our delta H was negative. So when do you use this Gibbs energy? Because Gibbs energy, you look at the balance between delta H and delta S. We had one favored, one not favored, so then we had to figure out what would be the answer to that. All right, so far so good? Okay, beautiful, and we're going to keep practice problem next time. We do nothing but practice problem next time.